started here. I guess I'll call this part 2. And we were working on, and so let's go here to number 5. But also let me take this as an opportunity to point out here that number 5 is really this next chapter here, which is our chapter 34. And so even though I haven't really got a chance to talk about it, we will here real soon. And so it's kind of weird saying let's do a review, because this isn't really a review. But what I would like to show you is kind of the end results. And I'll, again, call this instead of a review, a preview of what's to come here on Tuesday. And so let me put on the board that we are missing one final piece to our electromagnetics, as I hinted towards already, that we have Ampere's law, and a brilliant guy named Maxwell noticed a missing piece. And so again, let me just preview of what we will have our discussion on Tuesday, and let me give you some of the final pieces, because that's what this problem focuses on. And it'll be fun even on Tuesday to hook up a little radio transmitter, because here's what Maxwell noticed. And so I'll ask you guys, since I already gave you this preview, what are the 2 ways to make an electric and a magnetic field? Let's start with electric. What are the 2 ways to make an electric? Charges and changing magnetic fields. Okay, so we've covered that in great detail. And now, what are the 2 ways of making a magnetic field? Current. Okay, and that's the one we've covered in great detail. And then what's the new one? Changing electric fields. And what we're going to do is we're going to see, and this picture I think illustrates it quite well, is that on this side of the room, I am going to take a little circuit with a bunch of wires, and I am going to put current through it. And the current will be changing. So what would that current make? Well, if it's a current, shouldn't it make a magnetic field? But if the current is changing, the magnetic field it should make should be changing. So let me ask you another question. Not only would there be a magnetic field being made by the current, that magnetic field is changing, so what is that magnetic field doing? Making an electric field. And then what's that electric field doing? Changing, so it's making a magnetic field. And then what's that magnetic field doing? Changing, so it's making an electric. And so we're going to study this picture in more detail, but what we're going to discover here is that by having a little bit of current here, it will make a magnetic field, which will make an electric field, which will make a magnetic field, which will make an electric field, which will make a magnetic field, which will make an electric field, which will make a magnetic field, which will make an electric field, which will make a And so if I'm 93 million miles away, could I tell the effect of that current over there? Yeah, and why'd I pick 93 million miles? Because that's the distance of the sun. What's happening in the sun right now? It's creating a lot of fields, right? Some of you know a little bit more about optics. What's light? Isn't it an electromagnetic wave? And so if I start at some position right here, then some distance further away, and of course the field gets smaller and smaller the further I get away from it. But in class, we'll just set up a little radio receiver right here, and we'll set up a little transmitter right here, so it doesn't have very far to go. But when it gets over here, I claim that there's going to be an electric field where my receiver is. that is picking up the effect of the currents over here. And that's what this picture is trying to say. And so that's kind of my preview. You can imagine there's more details we're going to have to work through here, and there's some mathematics we're going to have to go through. But without going through all the detailed mathematics today, I will say then that this right here, this changing electric field makes a magnetic. And then when you incorporate that with Faraday's law, which says that a changing magnetic then makes an electric, one creates another, which creates another, and so at some significant distance away, we may have these fields, and essentially that's what you're doing with a telescope. You're picking up a very small electric field that came from light years away. Yeah.
So you're saying a photon is basically that? It's just like two
Yes.
fields in sync with each other?
Yes. That's exactly what I'm saying. And some other things too, so I'll... Right. And so this is what light is. This is what a radio wave is. This is what X-rays are. This is what microwaves are. And hopefully then when we talk about this on Tuesday, and that's what section 7 is to point out that all these things that we call light waves and radio waves and microwaves and X-rays and gamma rays are really the same thing. They're just different frequencies. And so what's the difference between red light and blue light? Yeah, just the frequency. That's just your brain saying, hey, that electric field is hitting the retina of your eye, and if it's a low frequency, your brain calls it red. If it's a high frequency, your brain calls it blue. If it's a middle frequency, your brain calls it green. If it's so low, your brain doesn't pick it up, and we call it infrared. If it's lower than that, we can't also pick it up with our eyes, but we can pick it up with an antenna. And so if there's an electric field over here and I take a wire, wouldn't that electric field make a voltage in this wire? And so a very simple antenna is to just take a wire and hold it up. And that means that somewhere over there was originally some current which made a magnetic field, which made an electric field, which made a magnetic field, which made an electric field, which made a magnetic field, which made an electric field. And then someplace where I'm holding this wire, there would be a voltage in this wire because of the electric field that is at this spot that, of course, was a consequence of what was going on earlier on. So a lot of fun discussions, and we'll build a little transmitter and receiver and have discussion and run through a couple pieces of math.
So that straight wire you said using an antenna, the photon has to be parallel to the antenna.
Let's not call it a photon because, again, we can think of light as either a particle or a wave, and in this model, let's think of it as a wave. The photon is a particle pitcher.
So the way it's propagating has to be like parallel with the...
Oh, yeah. Right. And if the wire is off of that, then we get a component of it. So if it's 90 degrees, we wouldn't pick up anything. Yeah, I'm glad you say that. I'll actually show you that with the antenna effect. That's nice to see too on Tuesday. But I think that's enough preview to make sense out of this question that is on the review here. Review. And so it says this. An AM radio station broadcasts isentropically, that means equal in all directions, with an average power of 4 kilowatts. How much voltage would be produced in a metal rod, let's call this the antenna, that is 65 centimeters long and 8 kilometers from the transmitter? Okay, so here is the transmitter, and it's going to send it out. Now, a couple things we're about to learn, and so again, I'll do this problem, but I'm a little hesitant because it's not really a review as much as a preview. But we're going to learn that the intensity is equal to the speed of these. And so we're going to use the symbol C for the speed of light times their energy density. And maybe I should spell this out here. Energy density. Now, why do these waves even have energy? And that we do know. We haven't done much with the energy density, but doesn't an electric field and a magnetic field have energy density? Yeah. Anybody remember the equation for the energy density of, say, the electric field? 1/2 mu naught E squared. Look familiar? Yeah. What's the energy density in the magnetic field?
1/2 B squared.
Yeah, B squared over 2 mu naught. Right? All right. And so, these waves, as they travel along, carry with them energy, because if there's an electric field, there's energy. If there's a magnetic field, there's energy. So in this case, we have both. Yeah.
Because both of those added together.
Right, and so in our case, if we want to know what is the energy, we've got to have both of them, because some of the energy is electric and some is magnetic. Now, it turns out, and again, maybe I'll do this without too much effort because it's not really obvious and I don't think we're quite ready for it, but those two numbers are actually equal. The energy in the electric field and the energy in the magnetic field are the same amount of energy. So let me do this, and if you're looking there at the solutions, you'll see what Don did. He said that instead of writing this as C times 1/2 the, and did you notice he put, well, he didn't put RMS squared plus B squared RMS over 2 mu naught. He said those two energies are equal. And so let me just do this. Let me just forget the term for the magnetic and just double the electric. All right. So I'm going to get rid of the 1/2. That would be doubling it, and get rid of that. All right.
Is that a C or?
Oh, shoot. Sorry. Yeah, that's a C. He then does one more thing, and this actually is very helpful because you guys know this already. If this field is changing, we could talk either about its maximum or its RMS. So if you're talking about the intensity, that's an average. That's why I put RMS here. But what did they ask in this problem? Well, I guess they just say how much voltage. And so my question for you is, do you want to calculate the RMS voltage or the maximum voltage?
However you're going to ask it on the test.
But aren't they related by that factor square root of 2? And I just realized it doesn't really say which one. But I thought Don had worked out the solution for the maximum. Where is the solution to this one? Yeah, he does the maximum. And now I don't know why he did the maximum. Does anybody? Does anybody care? I'll follow his and do the maximum because it just says how much voltage. So I'm going to take one more step. What is the relationship between RMS and maximum? Right, that's square root of 2. So I'm going to take the square root of 2, multiply it by the RMS, and square it. Oh, sorry, I did that wrong. That's not what I wanted. I want to take and substitute in the maximum. So if I put the maximum over the square root of 2, that would be equal to the RMS. And so I think Don has C times 1/2 epsilon naught times the maximum field squared. And that's the math we're going to do on Tuesday. Because this right here will allow me to solve for the maximum electric field. And we are how far away? 8 kilometers. Now, maybe I better talk about the other side of the equation, because I'm not sure how familiar you are with the word intensity. What's intensity? Do you know? Yeah, it's the power spread out over some area. And so for those of you who've done the 123 with the optics, we talked a lot about the intensity. We did that for sound waves too, for those of you within 123. But I don't think we did intensity this semester. Yeah.
What happened to the b squared?
The what?
B squared over 2.
This?
Uh-huh.
This and this are equal.
Oh, so that's what you've done.
So I'm going to drop this and double that. And again, I mostly did that without any proof. That's, like I said, it's kind of a preview of what to come. Because I think Don just starts the problem with what I would expect on the test, is you would just start off by saying, here's the power given in the problem, here's the area that it's transmitted, here is the C, here's the 1/2, here's the permittivity of free space. I can find then the electric field. In fact, let me put in those numbers. I'll start with the left-hand side. How much power is being radiated by this transmitter in this problem? Okay, so 4,000 watts, I think is what it said. 4 kilowatts, right?
Yep.
Okay. It's spread out over what area? Okay, so if I have this transmitter and it goes out equally in every direction, where is that energy spread out? Yeah, isn't it a sphere? So all that is spread out on the surface of a sphere. How do you calculate the surface area of a sphere? Yeah, it's 4 pi times r squared. And so there's my little transmitter. It goes out here and it goes out in all directions. And so that energy is on the surface of a giant sphere. And it was 8 kilometers, yeah. So 8 kilometers. So there's the power spread out over some area. And of course you can see now that as the distance from the transmitter gets further and further and further, the intensity is going to go down. And of course this other side, these are maybe not so obvious yet. Does anybody know what C is? Yeah, good. And that's, again, what we need to talk about. This is the speed of what we'll call electromagnetic waves. You might know it as the speed of light, but I think a better description of it is electromagnetic waves, because early scientists discovered it first for the speed of light, but what you're going to see on Tuesday in our little hour discussion here is that it was Maxwell who figured this all out, that, wait a minute, what light really is are these electromagnetic waves, and what color really is are these different frequencies of these waves. And therefore we can build things like radio waves and X-rays and gamma rays and microwaves and all these other frequencies that we didn't know existed. We can only realize the ones we have been able to see with our own human eyes. And so our own human eyes had this very narrow range here. And so that, unfortunately, I'm giving away kind of a fun discovery that Maxwell just discovered by going through the math. And you guys won't be as excited now on Tuesday when we do it. But Maxwell gets real excited when he goes, oh my gosh, look what this calculates out to be. And discovers the speed of light in electromagnetics. And so that's a big step. Anyways, I'll take the 1/2. And then the permeability of free space, 8 times 8.5 times 10 to the minus 12. And then we will have the answer that we were looking for. What is the value of the electric field 8 kilometers away? Yeah.
So does the length of the receiving antenna not matter, or why did they give us that?
Oh, I'm not done. This is just the electric field. The question asks, what's the voltage?
Oh, okay.
Yeah. So I don't need the length of the antenna yet. That's coming up. All right. So if I start over here, I've got 4 times 10 to the third. Then divide by 4. Divide by pi. Divide by 8,000 squared. Then if I divide by 3 times 10 to the 8th, then if I multiply by 2, then if I divide by 8.85 times 10 to the negative 12, and then if I take the square root of all of that, I get about 61 millivolts. And, volts per meter, sorry. 65 volts per meter. It's got to be an electric field. And so that's the electric field. Then your question can be answered. Yeah.
Would you guys kind of like the same answer for magnetic field but different modes?
Oh, I might as well give this away. Yeah, if we had done it for magnetic field, we would have replaced this with B squared over mu naught. And of course, then we could also have gotten what is the value of the magnetic field. And so when we build our antennas, which again, probably best to talk about this a little more on Tuesday, but when we build our antennas, we can then build the antenna to couple into the electric field or to couple into the magnetic field. And if you're just taking a metal wire with the electrons going up and down, that's probably best by saying, let's look at the electric field. But if you have like a loop, then the magnetic field can go through it and induce a flux, which could induce a current. So then we would have a magnetic antenna. So we can build electric antennas or we can build magnetic antennas. You're probably more familiar with electric antennas, and that's what this problem is. Yeah.
So they gave us the 65 centimeters long.
Yeah.
Did we have to use that for?
Yes. So the next step is to use that distance, because remember, and of course I guess this gets us back to chapter 26, the voltage is the summation of the field over some length. And so the voltage is adding up that. Or to make it simple, for a constant field, and I say constant over space. So at one moment, the field is a constant over my antenna. This would just be electric field times the length of the wire would give me the voltage. And so I have 0.061 volts per meter for my field. And the length of my wire is how long? 0.65 meters. And so that's the last piece that you were asking about. Why do I need the length of that wire? So 0.061 times 0.65 give me 0.040 volts. Although, that's not the number I remember Don getting. What did Don get here? 40 mil. Oh, good. We got the same number. Yeah. I just didn't remember that. But that's the length of it. So the big piece is really this. And to be quite honest, this might be more than we'll get a chance to do on Tuesday. So I'll preface this with this might be a little too much to ask for you guys for this exam. I do know this, that I will not put anything on the exam on Thursday that we don't get a chance to cover on Tuesday. I think I've said that many times in the past, and we'll keep saying it, that it just depends how far we get. Because I think this is actually section 4, and I really don't see us getting to section 4 of chapter 34. So we'll build the transmitter and talk about that, and we'll see how far we get. So ask me again on Tuesday, but I'll say it now that this last problem involving this chapter will be something that will only be whatever we get a chance to cover on Tuesday. All right. Well, that was a hard one to do, because again, it was something you haven't seen before, and it was more, like I said, of a preview than a review. All right. Well, shall we try the other test here? Oh boy. Let's try these 5 problems, and we'll do it in 17 minutes, right? All right. Well, we'll see how far we get. And you guys can come and go as you need, and we'll keep going. But fortunately, this one we have seen before. This gets us back to the beginning of our derivation. This asks for the equation of the inductance here. And so this object is built like a toroid. And so unlike the one we did an hour ago or so, well, we built a solenoid, and we asked for what was the equation for the inductance of a coil. This is that same question. What is the inductance that something has a shape of a toroid? And so it has n turns, and it actually is a little easier because it says show that it is equal to this. And so at least it gives you a chance to do it. And it does one thing better. It actually gives you the equation of the magnetic field in a toroid. So on the board here, let me draw this little section over here on the side. And so I'll go number 1, and I'm going to build this rectangle here. And this rectangle, one thing we learned is that the magnetic field in this toroid would be going either in or coming out, depending on which way the current is going. Let me just draw a field going in so that this would be the flux at maybe this moment when the current is going this way. This may be a DC circuit, or it may be an AC circuit, so the current changes. It doesn't really matter. That doesn't change the inductance of it. And like I said, I'm just going to draw that. And I don't know if I gave this enough space, but do these look a little closer together than these, I hope? Because the magnetic field depends on the distance r, where r is measured from the center of the donut hole part of this. And so if you remember the first example, no, I guess it would be the second example we did, we derived the magnetic field inside a toroid. We did an Ampere's law. So let me not repeat doing an Ampere's law, which we don't need to because they actually give the magnetic field for us. But that equation said then that the magnetic field would be strongest here at the inner radius, which is referred to as distance A, and then it would get weaker as we got further out to distance B, again according to this equation R, where R is measured from the center of the donut hole part of it. And so if you want to calculate the inductance, let's just take Faraday's law, which says that the EMF, which is equal to the number of turns times the change in flux. And if we go through a bunch of work and get something times di dt, then all of that something is the L. That's where the inductance came from. That was our whole argument, that inductance is a subset of Faraday's law. Faraday's law is then, or inductance is Faraday's law applied on itself. Okay, so let me go ahead and run through this. So here's the number of turns in the toroid. And now I need to calculate the flux through itself, because that's what inductance is. It is a Faraday's law back on itself. It's a self-induced EMF. And of course, when we did this an hour or two ago, well, it must have been 2 hours ago because it was our second problem, of course, we had the magnetic field from a coil because we were using a coil. But now we have a toroid. So let me do the same type of mathematics, but let me apply it to the toroid. And of course, for the toroid, we need to know the magnetic field. So again, the magnetic field is given. It's right there. So I'll put in the equation for the magnetic field, but I'll also at the same time put in an angle of 0 degrees. That again I get from the chapter 30, knowing that the flux is along the tunnel part of the toroid, and dA is, of course, in that same direction. And so that is the 0 degrees, which is great because as I look at this integral and the derivative, things that are constant I can pull all the way out. So there's another end to match with that end. There is the permeability of free space. There is then this 2 pi, and the current would change with time, or at least could change with time. And so I'll bring it in front of the integral, but not in front of the derivative. And then I have this integral of the area. And I still have the R because the field changes as you get further out. And so as this little picture is trying to show, if you take a little area, dA, it would be this height. And then you would multiply by a width of dr, and you would add all those together to get the total flux. And so this is going to be h dr, and we're going to add up from the inner radius A to outer radius B. And then once I do all that, I have the n squared, the mu naught, the 2 pi, and then the h I can bring all the way out. And the integral of 1 over r is the natural log of r evaluated from b to a. So here's b to a. And then the last piece of the puzzle is di dt. So that's the EMF. And of course, if you compare that to our definition of inductance, everything else, and then the current, then this must be everything else. And so just like we got it for the coil, we also got it for the toroid. And hopefully that matches. Let's see. I got an n squared, I got a mu naught, I got an h, I got an ln, b over n, and a 2 pi. Yes. I don't have a what?
No, why is there no DI?
Well, that's not the inductance. The inductance. Yeah. So canceling that with that and that with that, that equals that. Right. And so that is the inductance. And so if I, had the dimensions of the toroid and the number of turns of the toroid, then I can get the inductance of the toroid. Then I can hook it to, say, some kind of voltage, like a 25 volt source, close the switch and ask, what is the current, a microsecond later? Or how long does it take to get to half its maximum current, like that other one asked? And you have to get to the inductance first. And so there's Faraday's law and self-inductance kind of wrapped up together. Let's try number 2 here. Number 2 is looks like it is an RL circuit. And so I have a resistor and an inductor. Actually, it looks like I've got 2 resistors here. But it says study the RL circuit above. Okay. And maybe I'll even kind of repeat it here so I can kind of draw here. But it looks like this is a 25 volts. This is then a switch. This then has 10 ohms. And this then has an inductance that looks like it's in parallel with a resistor. Oh, now I hope they don't ask me anything too complicated here, because I will repeat what I said in class. We only had enough time in our circuits to do these in series, and I would not put this and say ask for the current at any moment in time. So I hope that's not what they ask. I hope they just ask the easy parts, like what is the current right when the switch is closed, or if it's been closed for a long time, or some others to that effect.